In Part 2 of Lecture 1, we will discuss the origins of operating systems. To understand what operating systems seek to do, you have to have a basic understanding of how computers worked back in the early days before operating systems. Computers were huge machines that ran one program at a time. Programmers entered their programs either from a console, often entering them by flipping toggle switches, or from punch cards or paper tape. Then the program would run, and the answers would be wrong because the program had a mistake in the logic or in the entering of the program. That meant sitting at the console and checking values in various registers and memory locations. It could also mean checking memory to make sure that the program had been entered correctly. Debugging was an involved and tedious job, and it all had to be done at the computer. By the way, it was this kind of checking that led to the term computer bug. In checking an erroneous program on the Mark II, Grace Murray Hopper discovered that a moth had gotten caught in one of the electromechanical relays. Since the relay couldn't close completely, the circuit was still open. The first computer bug was caused by a real bug. Eventually, it became obvious that this was not the best way to maximize the use of an extremely expensive piece of equipment, so they started printing out the contents of the computer's memory, what became known as a core dump. Programmers could then check their programs against what was stored in memory, and to ensure that it was what they had written, and then they could check memory contents to make sure that test data produced the results that they had wanted. Thus, programmers could debug their programs without having to tie up precious computer time. Several years ago, I took a course at Intel about Unix device driver design. Device drivers are the software routines that control various input-output devices, like disk drives and mice, and so on. The instructor in the course started by saying that you find a device as similar as possible to the one for which you are writing the driver, and then you make whatever changes that you have to make to convert it into a device driver for the new device. The moral of the story is that device drivers are difficult to write, and nobody really wants to write them unless they really have to. In the early days of programming, programmers had to write all the software, not just to do their calculations, but the routines that read data from the input devices and that wrote data on the output devices. This required a great deal of familiarity with the computer's hardware, and these routines took a great deal of time to develop. Programmers started saving the code that they wrote to simply avoid reinventing the wheel. In due time, they compiled large libraries of software procedures that could do all the common tasks that they had worried about: input and output, loading programs, assembling programs, linking programs. And this is how systems programming started, with a disparate collection of routines that handled all the hardware-related tasks. These same tasks became more complicated when compilers entered the picture. While programming in Fortran, COBOL, and other high-level languages simplified the job of writing a program, they complicated the job of running it. It was no longer enough to simply enter the program. You had to put the program on punch cards or paper tape, load the compiler, load the source program as data for the compiler, save the object code it created, load the object code so that the computer could run it, and then voila, you could finally run the program. If you were really lucky, the person ahead of you left the computer with the compiler that you needed loaded in memory, But this didn't necessarily happen too often. That meant that everybody had to load this huge amount of setup work. And since most people were not necessarily that handy, it could take a lot of time on occasion. Then somebody got the bright idea. Hire an operator, someone whose entire job was to take other people's programs and run them on the computer. Before there were operators, people might sign up for computer time by the hour. If someone used 45 minutes, the computer might sit idle at great expense for 15 minutes. If someone else needed 75 minutes, he or she might have to come back later to get that extra 15 minutes. An operator eliminated these inefficiencies. He, usually it was a he back then, would simply load the compiler, compile, link and run the program, and provide the programmer with a listing, output, and a memory dump. Then he would do this for the next programmer. Eventually, program operators figured that if they changed the sequence in which they ran programs, they could avoid loading and reloading the same compilers over and over again. So instead of running a Fortran program, a COBOL program, and then another Fortran program, they would simply run the two Fortran programs first before loading the COBOL program. This was a much more efficient way to use an extremely expensive piece of equipment that many people wanted to make use of. Eventually, someone got another bright idea. Write a program that would do a lot of the work that operators did. Loading compilers, loading and running programs, and printing their outputs and memory dumps as well. Thus was born the operating system. The earliest operating systems were all batch systems. The program and its data were all loaded at once. The program was compiled, loaded, and executed, and the program listing and the output were printed at once, usually together with a memory dump, if it was considered necessary. This might not have made the computer seem very user-friendly, but it did make the use of computers much more time efficient. The operating system routines remained in memory, usually at low end of memory, that is, the lower memory addresses, and then the rest of memory was available for the user program that was in memory at the time. In this environment, the operating system's main job was to determine which jobs should be read into memory next, read the control cards to determine which compiler would be used, or if the program was already compiled, which program's object code would be loaded, compile and load the program, find and read in its data, and then run the program. What you see here is a series of computer cards that might represent a student program running in the 1960s or 1970s on a batch system. The cards beginning with // are control cards, and the control card interpreter will process them. The first card identifies the beginning of a job. The second card instructs the computer to execute the what-for Fortran compiler, and that the cards that follow until the next control card are part of a Fortran program that will be running. The card marked // data indicates that the subsequent cards contain data for the Fortran program until the next control card. That control card is // end, indicating the end of the job. In a sense, the control cards are a program in their own right for the operating system, telling them what to do. In this case, use the what-for compiler to run a Fortran program with a particular data set. If the programmer wants to make changes, the program has to be resubmitted and run all over again. The big problem with running a program this way is that the computer's CPU spends most of its time idle. It takes time for the computer to read computer cards. Even a slow CPU will take a few microseconds to process instructions, while a fast card reader will only read 1200 cards per minute, which is about 20 cards per second. That time difference, which is about 1,000-fold, means that the CPU will spend more time waiting than working. One obvious solution is to move as much of the input-output work offline as possible, and have input read directly into the computer's memory. This way, the computer can work on other things while it's waiting for input to finish. The most classic example of offline operation is spooling, a concept that originated at IBM. Spool stood for Simultaneous Peripheral Operation Online. The input is read directly onto disk, and the input file waits until the CPU is ready to process it. When a spooled program runs, all input and output comes from and goes to the disk. The output is written into a different file that will eventually be printed. Even if disk I/O is still considerably slower than the CPU, the time difference is significantly less than that for a card reader or line printer. The printer may not even be available right away. Other output jobs might be printing at that time. But in due time, the printer will become available, and the printer will print the output file created for the job by the CPU. And all the time that the printer is working, the CPU is working on other jobs. Spooling may seem like an anachronistic concept, but it is still used today because printing is still slower than the CPU, and most computers only have the printer in active use for a small percentage of the time that the PC is actually being used by a user. Spooling means that several PCs can share a printer and even print jobs at the same time. The spooler simply saves the other jobs until it is ready to print them. It becomes very clear very quickly that the great disparity in speed between the CPU and input-output devices can make computer usage very, very inefficient. It seems that the CPU, even with offline operations like spooling, spends most of its time waiting for output or input to finish. This just doesn't make sense considering how expensive a resource CPU time is. A real-life analogy might be having your lawyer call someone for you, leave a message for that person to call him back, and then sit and wait for the return call, and bill you $500 an hour while he simply sits and waits for a call back. This makes you realize what a colossal waste of time it is. In real life, we would expect our lawyer to drop the matter for the moment and start working on something else for someone else so he could bill that other guy $500 an hour. Shifting to some other task while he waits for a callback is what people do in real life. Why not have the computer do this same kind of thing? We call this multi-programming, and the reason that it works so well is that all programs spend a significant amount of their time waiting for input or output. As soon as they request I/O of the operating system evicts them from the CPU and schedules another program to take over until that program needs I/O. As soon as the I/O operation is completed, the program will have the opportunity to resume execution. And in this way, we get maximum use of the CPU. Another advantage and another challenge of multi-programming is that now we will keep not one, but several programs in memory at once, which makes it easier to transfer control from one to another as they get bumped from the CPU while they wait for I/O. It saves us the time that it takes to save memory contents on disk and read in the core image of another job. But it creates another problem. How do we keep each program from getting into each other's hair? We need a better memory management scheme than what was used to keep application programs out of memory reserved for the operating system. Now we need to limit programs to a very specific area of memory. This is something that we will spend more time talking about later when we discuss memory management.